Can please get your attention? So we're just gonna do a quick little recap on what we were working on last time to get us back on page and wrap up our packet today. We might be able to start the new one, but if not, we'll do that on Wednesday and continue on with that packet. But what we did last time was instead of using a graph to help us to calculate the limits of our functions at different points, we were able to do this algebraically instead through our rules. So let's just remind ourselves of our rules here. So if we have a constant, just a constant all by itself, regardless of what x is approaching, my y values are always the same, that same constant. So I have the limit of a constant, regardless of the x value, I get that constant back out. If I have x as my function, then I get back the x value, right? As x approaches a, your x approaches a, so that's exactly what your limit is. And then these are a little bit more general versus those specific ones if with a constant or that parent function of that y equal to x line. Here are some things to be mindful of is that these rules only work if both the limits exist, which really just means gives you back a real number, right? If either one of them does not exist, we are not allowed to use these rules. It doesn't tell us that what happens to the limit. It just tells us these are not the ways to approach that limit if that's the case. Something else to point out is that all the rules we have here are for overall limits, but they're also true for left-handed or right-handed. So if I put a minus in the power on all of these, the rule is still true. So some ways that we're going to see today, if one of my limits doesn't exist, I could instead study the left-handed limit, decide maybe there the limit does exist. I can use my, let's say, product rule, and find my right-handed limit and then check, do they agree, right? Because in general, my overall limit exists if both sides approach the same exact number. So if both sided limits exist and are the same, that's another method for me to solve for it. If at that specific point, the limit doesn't actually exist, right? I can still do some work with that to be able to use these rules here. So where I see plus or minus, I can separate my limit with my plus or minus. If I see a constant multiple, I can move the constant to the front. If I see a product, I can separate with my product. The only one to be very cautious of is quotient. If the limit of the denominator goes to 0, we're not allowed to use it. Again, that doesn't tell us what the limit approaches. It just tells us we can't use this rule. And then we have things with powers, which is really this repeated product. So I can do things like my product rule over and over again. So if I have a function raised to a power, I can instead think, what is the limit of the inside? And then raise that to that specific power. This also works with the roots. This is really the same as like a power of 1 over n. The only places there to be cautious of is if that n is even, I can't plug in negative values. So this rule only works if this inside piece is positive for n even. If n is odd, I can have whatever number inside, and I can actually evaluate that there. So we went through some examples solving our limits algebraically. And what we found is for polynomials, these work the nicest. Polynomials are really just a bunch of powers, constant multiples, sums, and differences. So essentially, when I see a polynomial, I can just plug in, right? I really do get the same exact value nearby as what happens at that specific point. That idea is this idea of continuity, which is the next packet we'll talk a little bit more about. Something similar for rational functions. So if I have a polynomial over polynomial, I can just plug in as long as my denominator does not go to 0. So if it's in the domain of the rational function, then I can just plug in, and what happens nearby is exactly what happens at the point. If I get 0 in my denominator, I can't use that rule. And we actually saw some examples of ways to tweak our functions to be able to solve for those instead. So here was an example where I got 0 over 0. I cannot use the quotient rule. But what I can do instead is I can tweak my function so that it differs only at the specific value. So my functions are the same everywhere except that x equal to a. What happens nearby is exactly the same, so my limit should be the same. So when I have a polynomial over polynomial and I get 0 over 0, immediately what that's telling me is that my a value here is giving me information about a root, and so giving me information about a factor. So I can factor out x minus 3 or x plus 3 from the numerator denominator, cancel out, and I no longer have 0 in my denominator, and I can use my quotient rule there instead. All right, so there's a few different ways that we can manipulate our function to make it easier so that we can actually use our rules and apply those there. Okay, so last thing that we did was we're gonna now combine the rules that we have algebraically and with our graph. So here I just have in my graph my function f and my function g. And I'm gonna find the limits of different combinations of f and g, some with sums and differences, constant multiples, some with products and division. And what we're going to see is that we can't always apply the overall rule, the overall limit rules, but we can look at left-handed or right-handed limits to give us the full information. Okay, first one, we saw constant multiple and we saw addition. So we separated these. And eventually you'll feel comfortable enough to just do it all in one step. And now we want to see at x equal to -2. I know what happens to my f function and my g function. I get one exact value there, so I can just plug it in. Right, so here at x -2, my f function nearby goes to 1. I don't care what happens at the point. The limit just cares what happens nearby. Versus for my limit of g, I get exactly this -1 value here. So I can just plug in and then compute that and simplify to give me back -4. Okay, so before we do number 2, do we have any questions on our rules or any of these examples that we went through on Friday? Alrighty, so the next one we have is about a product. So first thing we want to decide is, can we use our product rule here? So here we look at x equal to 1. We see for our function f, it approaches the number 2. But for our function g, we have this gap here. On the left, it approaches a number. On the right, it approaches a different number. So my limit does not exist at that specific point. So I can't use this rule here for products for my overall limit. This does not tell me I can conclude something about the limit. I don't know if it exists or it doesn't exist. I have to do some other work to be able to solve for it, to be able to compute it. So what we do is we're going to study the sided limits. We're going to see what happens on the left-hand side of this limit. We're going to be able to see if we can use the product rule for sided limits to solve for it, and then decide what happens if I did the right-handed limit instead. If they agree, that's what the limit equals. If they don't agree, then I can say the limit does not exist at that number. So that's what we're going to do here. So I'm going to write LHL for left-handed limit. And so all I'm doing, instead of looking at x approaches 1, I'm looking at x approaches 1 from the left. And so how do I signify that in my notation? What do I write for a left-handed limit? Yep, I want a minus sign, and it's going to show up in the power of my 1. I don't want to confuse that with -1. Right, it's coming on the right, it's on the other side of my 1 here, right? It's not telling me the sign of the number, it's telling me the side I'm approaching. So left-hand side here. And my functions are still f and g. And now I want to decide, can I use one of my rules to compute this? So can I use my product rule, but with left-handed limits instead? And as long as both of these limits exist, then I can use that rule, and these should all be left-handed limits. So our first goal is going to be deciding what are the left-handed limits of both of these functions as x approaches 1 from the left. So here's my 1, and I care only about the left-handed direction right now. So for f, what do I get? Do I get a value here? Yes, I get 2, right? As I approach from the left, I get back 2 that from the right, it's the same. But right now, I just care about the left-handed limit. So I have a 2 times. And what about my g function? What happens as I approach 1 from the left-hand side? What do I get? Yep, I'm gonna get my -2 here. I do get an actual value. Again, I just care about what happens on the left. So this is telling me I can use this rule because both of those give me back a specific number. If one of them was that does not exist, maybe because it's not defined near that number, maybe it shoots up to positive or negative infinity, maybe it oscillates, then I can't use that rule here. So I just multiply these together, and this is telling me my product on the left-hand side is going to go to -4. And now all I need to do is decide what happens on the right-hand side. If they disagree, the limit does not exist overall. If they agree, that's exactly what the overall limit will approach. So same idea, except now, instead of a minus on the power, I'm going to have a plus in the power to tell me right-handed limit. I still need to check, can I use this quotient rule, product rule? Do I actually get an answer for both of these pieces? Okay, let's see. On the right-hand side of 1, my f function still goes to 2. And what about my g function? It's going to give me back -1 here, right? Below my x-axis at 1, so this is -1 here. I don't care what happens at the point. I care about what happens nearby. So here I get a -1 for g, and I get a +2 for f. And because both of these gave me back an actual number, I can use my product rule on both of the pieces here. Okay, here I get a -2. So I found my left-hand limit gives me -4. My right-handed limit gives me -2. What does this tell me about the overall limit as x approaches 1 of that same product? What can I say if my left and my right-handed limits don't agree? Say louder. Doesn't exist, right? I need to approach one single value, right? So if I'm approaching 2 different values depending on the side, my limit does not exist. I can actually answer the question now. This original limit that I wanted does not exist. Since sided limits don't equal each other, don't agree. Right, my left-handed limit and my right-handed limit were 2 different numbers that I got here. Okay, this won't always be the case. There might be ways that we can look at these functions where at the point I can't use my rules, but left and right I can, and they end up agreeing, right? So we'll see some more examples. So anytime I can't use my overall limit rules, I want to look at the sided ones instead and see what information I can say there. Okay, so let's look at number 3. Now we're looking at the quotient g over f, and we're looking at the sided limit where x approaches -3, the power says a negative, so from the left-hand side. I want to decide what do these approach. So the first thing I look at is, this is a quotient. I want to try to use my quotient rule, but I have to check, can I use it in this case? We'll look in just a second. But I want to see, what does my g function do on the left-hand side of a minus, oh, this is a +3. +3 from the left-hand side. And I want to see the same thing for my denominator. Can you guys tell me, when can I not apply this rule? When it's 0 at the bottom, that's the more obvious one. That's the one we want to check more often, or if either one of these don't exist. Right, if one of them does not give me back a value, I can't use the rule. And if my denominator equals 0, I can't use the rule. So let's see what happens in these cases. What does my g function do on the left-hand side of 3? Here's my value 3. On the left-hand side, what does my g function do? That's my blue function. Get this value here of +1. And what about my f function? It goes to 0. Right, so here I have a 1/0. So this is immediately telling me I cannot apply this rule. But this is already a sided limit. I can't break it up into a smaller piece or look at left and right to answer this question. But it turns out we actually know what happens in this setting. Something else I'll point out is I couldn't have done the overall limit here because it's not defined on the right-hand side. So we also want to remember to compute our limits. It has to be defined near the point. Unless it's left and right, then it has to be defined on the left or defined on the right-hand side. But this is telling me now that we can't apply the quotient rule for limits. Because the denominator went to 0. Right? If the denominator was any other number, then I just get that fraction 1 over that number, and that would be my final answer. Okay, it turns out, again, we can actually answer this. Lots of times we'll just say does not exist, but this is one of those cases where I can give more information. So whenever I have a non-zero number, that's what this is saying, a number not equal to 0 over 0, my sided limits always go to plus or minus infinity. It turns out if the top stabilizes to a number while the denominator gets smaller and smaller and smaller, the whole thing grows rapidly to plus or minus infinity. The goal is just to decide, is it positive or is it negative? Okay, and so that's what my sided limits do. But if they go to opposite directions, one's negative, one's positive, then my overall limit does not exist, and that's all I can say. If they agree with each other, if they go both go to positive, both go to negative infinity, then that's exactly what my limit's going to be. And I want to give that extra piece of information. I don't want to just say does not exist if I can give a little bit more info on if it goes to positive or negative infinity in those cases. Okay, so what we can do here, since this is already a sided limit, is I know this is going to be plus or minus infinity. My goal is now just to decide, is it positive or is it negative? So this goes to plus or minus infinity. And our goal is to decide which sign is it. Is it positive or is it negative? Okay. My numerator approaches 1, a positive number. So this top part is just going to be positive up top. But in terms of my denominator, it's approaching 0, right? That's not giving me information on the sign, if it's positive or negative. So I'm going to look at my graph. If I approach 3 from the left-hand side, am I approaching it from the positive or negative? So are my y values positive or negative on the left-hand side of 3? So here, if I look to the left, my y values are above the x-axis. So these are all positive here, right? If I thought both directions, I don't have information on the right, so I can't answer that. If I went all the way through on the right-hand side, it would be negative. I get 2 different answers for my left and right-handed limit. But here, I'm just looking at left-handed limit. On the left, it's above the x-axis, so it's going to be positive here. So I get positive over positive, which is positive. So my answer here, instead of just saying does not exist, I can say it goes to positive infinity, right? If I actually had the graph of f over g, or g over f, I'd see on the left-hand side of 3, it skyrockets to positive infinity there. So anytime you have non-zero over 0, the side limits will be plus or minus infinity. You decide, is it positive or negative? And this will give you information about the overall limit as well. Okay, questions about this back here? How we're using it? Okay, so we could actually answer that question, just not using quotient rule. Quotient rule is not helpful here, but again, non-zero over 0 means sided limits go to plus or minus infinity. I just studied the sign. If I want to know the overall limit, then I decide, do they agree with each other or not? Okay. Other ways we can't use the quotient rule and where this is not going to work is if we have 0 over 0. We already saw an example of that where we had polynomials that we could factor and cancel and somehow get a number back out. So lots of different things can happen when we get 0 over 0. We can't immediately conclude it goes to plus or minus infinity. It doesn't exist. It gives me a number. It really depends on the situation. But anytime we have something like this, our goal is to manipulate the function. just like we factored and canceled, there's other forms of manipulation to slightly change the function so that it's doesn't agree only at x equal to a, but everywhere else it does agree. So I gave myself space in the wrong spot here. So I'm going to go above and below this little section here, right? We saw that we could factor. This is one way to manipulate the function, and then cancel so that hopefully there's no more zeros in your denominator. Something else we want to feel comfortable doing is getting rid of square roots, right? Lots of times we'll have square roots showing up, and if I can get rid of them, I can have polynomials show up instead and then do some manipulations like factoring to help me to simplify. So there's two different ways that this could happen. If I just have a square root by itself, what I want to do is multiply by the square root over itself. I want to multiply by something equal to 1, so I'm not really changing the function. And this will get rid of the square root from the numerator and really just moves it to the denominator. Okay, another way you can see square roots show up is if you had a square root plus or minus something else. So let's say that's your original. What we can do here is we can multiply by a conjugate. That's a fancy way of saying multiply by this, but just change what sign is showing up. So if it was plus, I turn it to minus. If it was minus, I turn it into plus. Whatever I do upstairs, I do downstairs. So I'll multiply by square root of minus or plus, where I swap the sign, and I do the same thing downstairs. So here where I write plus or minus and the minus plus is on purpose, I really want to change the sign to give me the conjugate there. It turns out this is actually very helpful because it gives us a difference of 2 squares, and it gets rid of the square roots that we're working with here. And most likely we'll give you back a polynomial instead. Again, we'll see more examples, explicit examples, but I just want to list some of these out here. And then one last way that we'll see is by combining fractions. So if I had multiple fractions, let's say that I was adding, we can combine fractions. By finding common denominators. Okay, but again, we'll see some of those examples later on in the packet, and we'll see some of those on the homework as well. But those are some typical ways that you could manipulate to simplify and actually solve if you're not allowed to use one of your other rules there. Specifically, if it's 0 over 0, these are the types of ways that we're going to manipulate them. Okay, so next up, we're going to get some more practice with left and right-handed limits. These are going to be especially helpful when we're working with what's called piecewise functions. So here our piecewise functions are telling me when my x is less than 1, I want to use this equation. When my x is between 1 and 2, including both endpoints, this is my equation, and so on. So we want to feel comfortable being able to use our piecewise functions as the functions that we're finding limits of without their graphs, right? We can do this all algebraically. It's all just about left and right-handed limits in these cases here. Okay, so something that I like to do, although this is already organized in the correct order, is I like to draw a little number line just to remind myself which pieces get which equation. So the first things that I'll plot are all of these endpoints that are showing up on my little domains here. I'm going to plot them, and I'm going to decide on the left of whatever number, what equation am I using? On the right, what am I using? So the x values that we have are 1, 2, and 3. So these are the ones I'm going to plot. Okay, and on my x less than 1, so this portion here, so to the left of 1, I want to use the equation x plus 1. So everything to the left, and am I including 1 or not including 1? Right, there's no equal sign, so I'm not going to include it. So here to the left, I'm going to use the equation x plus 1, right? I'm not graphing this information. I'm just trying to reorganize it to make it easier for me to decide what's left and what's right. Okay, for my my numbers between 1 and 2, And I'll do purple for this one. So including 1 and including 2 and everything in between, I want to use this formula, which just says for all those x values, my y value is always 2. I can think of this as my horizontal and my constant line here. Okay, in green, let's do the next one. My x squared function. I want to use this function when x is bigger than 2, except at 3. So every number bigger than 2, except the number 3 here. So not including 2, to the left, excuse me, to the right of 2, not including 3, and then continue in the right direction. This is what we mean by x greater than 2, not equal to 3. I could have also written this as between 2 and 3, and then bigger than 3 as well, if I wanted to write it as a union of intervals instead. For the green, we're using this x squared. Okay, and then the last piece is when x is exactly equal to 3, the output is just going to be 0. So here, when x is equal to 3, the exact value is 0 here. I can almost think of it as a horizontal line, but it's only happening at one point. So it's really just a dot filled in exactly when x is equal to 3. It'll be on the x-axis. Okay, this will give me the full information on what my left and right-handed limits will look like at these like weird endpoints that I have on my intervals here. Okay, so if I look at my limit as x approaches 1 of my g function, I have a lot of formulas I'm using here. I need to decide which one do I use, or do I have to study my left and my right-handed limits? So my x equal to 1. Here I'm saying on the left, I use this formula. On the right, I'm using a different formula. I can't just plug in whichever I want. I have to look at the left and right-handed limits to tell me what's happening nearby. If they agree, then that's my answer. If they don't agree, my limit does not exist at that point there. So we have to use left and right-handed limits here. Unless on the left and right, the functions were the same, then I don't have to do that because nearby, it's the same formula. But here, nearby, left and right, I'm using different formulas. I have to do 2 different limits to answer this question instead. So the places to be extra cautious about in piecewise functions are all of these values that are showing up here, these endpoints that are showing up in all of these intervals. So those are the places to be extra careful about. Right, if I had picked, let's say 1.5, it's the same function on the left and right. I don't have to do a left and a right-handed limit. I can just think about the limit overall all at once. So functions on the left and right of the endpoints can look different. So we need our sided limits. Okay, so let's look at our left-handed limit first. Okay, so here I'm going to look at the limit as x approaches 1 from the left of this function. So what I want to decide is, what does the function look like to the left of the number 1? And so here, what is my formula when x is less than 1? Yep, in my blue here, I have my x plus 1. So now, because I'm just looking on the left, and my formula is always x plus 1 on the left here, I can replace my g of x with x plus 1 instead. And now this is something I have rules to help me to find. This is a polynomial. I can just plug in my value, and it tells me what happens on the left-hand side here. So here, I'll get back plug in 1, and I get back 2. Okay, maybe I'll where it came from. This is my x plus 1 that came from the left of 1. And I have my right-handed limit. So I want to decide, what does the function look like on the right-hand side of 1? Which equation should I use here? Which color do I use? What's on the right of 1? Purple, this would be the function 2. This is saying for every x value there, the y is just 2. So this is a constant function. When I see a constant, that's exactly my answer. Right? My y value is always that exact number. So I do get 2 back out here. Okay, what can I say about the original question that I was trying to answer? What is the overall limit of this function as we approach as x approaches 1? Right, they agree with each other, so it has to be exactly equal to 2. If I got 2 different numbers or one did not exist, immediately the overall limit doesn't exist. But as soon as the sided ones exist and agree with each other, that's going to be my answer about nearby what's happening. So these agree. And so this is telling me the limit overall as x approaches 1 is going to equal 2 in this case. Okay, again, in piecewise functions, we're extra cautious of the endpoints because on the left and on the right, we could be using different formulas. Okay, so let's do the same thing with 2. So here I'm seeing for 2, I have a mixture of functions showing up. I can't just use one. Right, I see this as an endpoint. So I have to look at my left and my right-handed limits, decide what do they equal. If they agree, that's my answer. If they disagree, then it does not exist. So let's look at our left-handed limit. Now as x approaches 2 from the left, I need to decide what formula am I using? What formula is used on the very left of 2? Which color do I use here? My purple, which is my function 2. And when I see a constant, that's exactly my answer. So that was pretty easy. I just want to work with my right-handed limit now. Go ahead.
If we can think ahead and just see that's 2, would you still want us to write out like limit x?
Yep, I want us to justify the work, right? Because lots of times we could read the graph incorrectly. You understand the idea, but you plug it in incorrectly or something like that. So the answer in almost all your work is worth the least amount. It's the justification that gets you most of the credit on the problems. Okay, so next up we have our right-handed limit. Although doing that, just like trying to think ahead, will help you figure out the answer. So if it doesn't match what you did, then something went wrong there, right? So just trying to plug in these pieces into the individual pieces will help you to get you an answer as well. Yep. Okay, so now I want to see what happens on the right-hand side. And now here to the right of 2, I'm using the function x squared. So this is what I have here. And now this is a polynomial. So I can just plug in my value. And this gives me 2 squared or 4. So now I'm seeing here that these don't agree. They both exist, but one gives me 2, one gives me 4. In terms of the graph, what we'll see is a little jump, right? On the left-hand side for 2, it'll be filled in as 2. And then on the right-hand side, it'll be approaching 4. So they're really going to 2 different numbers here. So my overall limit doesn't exist because they don't agree with each other. So here I can say does not exist for my original question. Okay, questions on this one? Okay, let's think about as x approaches 3. What should we do here? Yeah.
Something that says x equals 3, but it's not exactly.
So we want to decide what happens nearby. It could be undefined at 3, and my answer should still be the same, right? I don't care what happens at the point. I care about what happens to the left and to the right, what happens nearby. So here nearby, what functions am I using? My x squared. On the left and on the right, I have the same exact formula. I don't have to split this up into left and right because nearby, the formula I'm using is x squared. right? If I wanted to, if I felt like uncomfortable just doing it all together, I could do left and right, but the work that you'll do is exactly the same, and you'll save yourself some steps recognizing that you only need to work with the overall limit because nearby the function, the formula you're using is exactly the same. So here we can find this limit by replacing my g of x with x squared, since on the left and on the right, that's what my formula says. And now this is a polynomial, so I can just plug in. And this gives me back 9, right? And I'm done. Much easier when I'm only working with one formula on the left and on the right. Again, I don't care what happens at the point, right? It can be undefined. It could be defined as a different number. My limit doesn't care what happens at the point, just nearby what's happening. Here, we can say since g of x equals x squared, near x equal to 3, we are allowed to just replace the g function with that formula. This is really saying the left-handed limit and the right-handed limit use the same formulas. So we don't need to split it apart to figure out what happens overall instead. And we want to remember the limit does not care what happens at the point. Right here, that was g of 3. We said that equals 0. It's completely unrelated to what the limit is looking for, what happens nearby. Okay. Any questions on how we used our left and right-handed limits here? Or why for these specific values we had to be more careful? Okay. So let's do our next example here. And here, right, my variable name is different, but it works exactly the same. My variable name is h. So in terms of h, upstairs I have a polynomial, downstairs I have a polynomial. So it's technically a rational function. But what happens if I try to plug in here? What do I get? Okay, I get 0 where? Yep, definitely downstairs, right? Because it's just h. If I plug in h equals 0, I get 0 downstairs. What about upstairs? I also get 0. So this is one of our examples of 0 over 0, where we have to manipulate the function to decide what it does, right? There's lots of different things that could happen. I can get a number, I can get does not exist, I can get plus or minus infinity, but I don't know right off the bat. Unlike when I get non-zero over 0, I know my sided limits are plus or minus infinity, and I just decide the sign and if they agree. So here, all the next couple examples are going to look like 0 over 0. And so we need to manipulate the function. Right, some ways that we talked about manipulating these are by factoring, or by getting rid of square roots, either through conjugates or multiplying by the same square root over itself, or by combining fractions, because we know what happens to a non-zero over 0, a 0 over 0, and things like that. Okay, but again, I first try to plug in, I see I get 0 in the denominator, I can't use the quotient rule, but then I notice 0 upstairs tells me I need to rewrite the function somehow. Okay, so what we're gonna do first is we're gonna rewrite the numerator, right? It turns out, since upstairs is really a polynomial, this kind of complicated the way that we wrote it. If I plug in 0 and I get a 0 back out, that's a root, that tells me what has to be a factor. And here my variable name is h. What would be a factor? I can ask the same question downstairs too. This is a polynomial on h. When I plug in this value, I get 0. So what should be a factor downstairs is a little more obvious. This is just h, or h minus the number H minus 0 is just H here. So we'll see after rewriting, we can pull out an H at the top and pull out an H on the bottom to cancel out, to get rid of the 0 from the denominator is really our goal here by doing this factoring. So here I'll have H minus 0 is a factor only because it's a polynomial that I'm working with here, right? If I had instead H approaches 2 and I got 0 up here, I would know H minus 2 would be a factor instead. Okay, so that's just something that we'll look out for after we rewrite the top. So here, if I expand, I'm gonna get my 9. I'm gonna get my H squared, right? This is my 3 squared. And what should go in between? My 6H. We wanna be really careful that we're not just squaring the pieces and then adding. I'm technically foiling here when I expand it. So I want to think what happens when I multiply these together. I did that twice to have 3H plus 3H or 6H here. If you're not as comfortable expanding, you can write a couple more steps in here, but just to save us some time, I'll talk through it, but I won't write every single step there. Okay, that's the first part. That's this portion here. And then I have my minus 9 upstairs. My denominator is unchanged. I can't really do anything else there. But what can I do to my numerator to try to simplify? Yeah, I can combine my like terms. I only have one H squared. I only have one H term, so I can't rewrite those. But I have a 9 and a minus 9. They cancel. And so I'm left upstairs with an H squared plus 6H. Okay, but I can rewrite this. Now it's a little bit more obvious that I can factor out an H upstairs and downstairs. And I'll write it below actually. Okay, so when I pull out an H upstairs, what am I left with? Yeah, I'm gonna get my H plus 6 or 6 plus H here. Right, I just see what do I need to multiply by H to give me H squared? 1H. What do I need to multiply H by to give me my 6H? Just my 6 here. And now my H is due at I'm no longer gonna have a fraction where I'm dividing by 0. I end up getting a polynomial. For my variable name now is H. But it works exactly the same. I can just plug in. So I get a 0 plus 6 or a 6 as my final answer here. Right, again, this is a polynomial. Where the variable is H. So we can plug in. Okay, so again, I had a polynomial over polynomial. I saw I got 0 over 0. So I should be able to factor an H minus this number, but I had to do some rewriting first to make it easier for me to see how to factor that out. Okay, we're gonna do another example where again, we get 0 over 0. We have to do one of our manipulation techniques. Again, factoring, getting rid of square roots, or combining our fractions into one single fraction to be able to solve for it as well. Okay, so again, you should always check, can I plug it in? And will I make sure that I don't get a 0 in the denominator? Then I can try to use my quotient rule. But here, if I plug in t, that was my variable name. If I plug in t equal to 0, I get a square root of 9, which is 3. 3 minus 3 is 0. 0 squared is 0, so we do get another 0 over 0, which tells me I have to manipulate the function to decide what this is approaching. But still, I get the 0 over 0 here. Okay, so of the 3 options, what should we try to do here? Which form of manipulation can we do? Am I going to factor? Am I going to get rid of a square root? Or am I going to combine a fraction? Yeah. Yeah. Oh, so we want to be careful. This one here is not the same as t plus 3 times t plus 3. right? If I could write it as something multiplied by itself, then the square root would cancel it out. But here, this is not actually a square, right? I can't write it as something squared, so the square and the square root don't cancel. But I do want to get rid of the square root. So this is an example where I see square root and then plus or minus something on the outside. This is where we want to conjugate, which is a fancy way of just saying, turn this into a plus. So multiply it by this with a plus and do the same thing in the denominator so that you really haven't changed the function. So we'll conjugate here, right? Plus goes to minus, minus goes to plus. So here, this is only about what's happening on the outside of the square root, not on the inside. Inside the square root stays exactly the same. And now the minus on the outside turns into a plus. And whatever I did upstairs, I want to do downstairs. And what's going to happen now is I'm going to get rid of all the square roots from my denominator. Doing this trick helps me to get rid of the square roots there. Although technically it's moving it to the denominator, but it turns out we can solve for it when this happens here. So my denominator is going to stay, I'm not going to expand it. I'm just going to leave it written as is. And we're going to write it as t squared times the square root of t squared plus 9, and then my plus 3 on the outside. Okay. And now I want to think about what happens when I multiply these together. Why was that the trick to do? And I want to be careful. I technically around here, I'm multiplying the entire numerator with this entire numerator here. Okay, can anybody tell me what ends up happening in the numerator? What if instead I had an a plus b and an a minus b? What would I get in this side? So in terms of a and b, if these were numbers, the a squared, I get an a times minus b, I get a b times a, and I get a b times minus b. So I get a squared minus ab plus ba minus b squared. How can I simplify that? Get the middle two terms cancel. They just have opposite signs, but the same number showing up. So this is the same as a squared minus b squared. This is a difference of two squares. So this is how to undo that process. Usually we take a difference of two squares and we factor. Now we're rewriting it so that we see the factors and we can write it as difference of two squares. The reason why this is helpful is I'm going to square this entire thing with the square root. The square root disappears. And these middle terms that should have had square roots cancel each other out. So I end up having no square roots left over. I have this squared minus that squared. Much simpler. I don't have to write all the steps. Unless I don't feel comfortable with it, then I'll write all the steps to make sure I understand why. But here I'll have the first term squared minus the second term squared. Then I simplify it. And again, my square and my square root now can cancel. Okay, so I just get what's inside the square root, which is a t squared plus 9. My minus, in parentheses, 3 squared turns into a minus 9. And my denominator, I'm not going to change. It turns out it doesn't help me to rewrite this. So I just leave it alone. And now I see things start to cancel. My 9 and my 9 minus 9 cancel. I'm just left with the t squared upstairs. Okay, my denominator stays exactly the same. What happens if I try to plug in now? Still 0 over 0. Here I get a 0, here I get a 0 because I'm multiplying. I don't even care what this is. I still get a 0 over 0. So I have to continue manipulating. Can we see how to manipulate this one? Does anything cancel? Go ahead. When I'm multiplying upstairs and when I'm multiplying downstairs by the same quantities, that's when I can cancel. I can think of this as a t squared times 1. This is a t squared times all of this. Now I can cancel out these pieces. I can't cancel if I see it in terms of an addition. It's a part of a term with addition in it. I can't cancel upstairs and downstairs. It has to show exactly the same upstairs and downstairs in multiplication. So here, these do cancel. So now upstairs, I just get a 1. Downstairs, I get what was in my parentheses. Okay, what happens if I try to plug in now? Clearly upstairs is just 1, but what about downstairs? Do I get 0? No, that's all I care about. I get a number that's not 0. I cannot use technically my quotient rule to plug it in. If I plug in 0, I get square root of 9, which is 3. Added to 3, I get back 6. So I get 1 over 6 here, right? Because this is not equal to 0, I'm technically using a quotient rule for limits. They both give me back a number, so I just get the numerator over the denominator now, right? I can really just plug in when the denominator does not equal 0. Okay, and we are out of time, but you'll see some more examples of these on the next homework set. Where we want to do these kinds of manipulations. The only one we didn't see in practice was one with fractions. So if I see addition or subtraction of fractions and I don't know what those pieces go to, I want to combine them to make it easier for me to solve those problems instead. But we'll pick up here on, what's today, Monday? On Wednesday, and then we'll actually start the packet on the continuity once we're done with this last piece here of the packet. All right, have a good one. The quiz number always matches up with the homework number. So quiz 1 will be homework 1 material. Yep.